the assumption, we're going to assume that we're using a singly linked list. And this is important because it will affect the time complexity of the different things we're trying to do. Okay, so let's say I want to insert the value of 6 into a linked list. And let's, for sake of argument, just say our linked list is already in existence. We have our head and pointer. This is pointing to, doesn't really matter, but let's give it some values, and we have our tail. Okay, so if we're just simply appending this, okay, if we're not trying to place this in a certain position, then what we expect to happen is, okay, we don't need to update the head because we're appending to the tail. Okay, then our new element is going to appear, what was it, 6? As the next element of the second element in the list, and we need to update the pointer. Okay, so the thing we should ask ourselves then, well, what was the complexity of that operation if we simply insert something at the end of a list? Again, assuming it's singly linked list. Any suggestions? Options will be log n, 1, n, and so on, n squared. Okay. What was the question? Okay. We're thinking about the time complexity of this operation. If we insert 6 at the end of a linked list that's already established, what is the time complexity of adding this? Yep, a couple of people have nailed it. We get a constant time complexity. That should hopefully make sense because all we need to do is access the tail, which is this element. Okay, so that's one operation. Then we simply add our next as being 6 and update the tail. Now, in reality, there's like several operations that happened there, but we remember that we just throw away those types of constants and then just simplify to say, well, it's constant time. Okay, we didn't have to traverse the whole list or do anything else like that. Okay, good. Okay, we'll try another one of these. Let's say we try to delete the head of the list. Okay, so again, we have a list. We have pointers to, we'll use the same one, 1 and 5, and it now has 6 on here. Okay, if we want to delete the head, well, we can see what it looks like. Head and tail, well, this is the head here. So this is what we want to remove. We know we have a pointer to it. So then we can simply just say, well, now this points to 5 instead. This now points to 6, and we didn't need to change anything there. Okay. Time complexity of 1 again. Excellent. Okay, so this is, we can see in this kind of application, this is where lists are pretty good, okay, because we get to use these pointers to get a nice speed up. Okay, let's delete the tail of a list. Again, assume it's singly linked list. We have the head and the tail pointers. Okay, so current status is 5 and 6. We know that this is the tail. Okay, so if we delete the tail of our list pointer, we're going to just have this situation. Okay. So in this case, when we delete this, what is the time complexity? Okay, a couple of people are suggesting n. In all honesty, is anyone thinking, what? I thought that would also be constant time because you're just updating the tail. It's okay to say that because this is the sort of thing I would think and easily get confused about. Okay, the way to think about it here is, okay, yes, it is fast to find out what the tail is. We find that in one operation. The problem is that we have no idea who the next tail should be, okay? There's no pointer back to 5, so we have to rediscover the tail of the list, okay? And because this is a singly linked list, we have no back pointers to the previous element. So the best we can do is then traverse the entire list, get to the element that is currently pointing to null. Okay, so we have this kind of, in reality, what we have is we can access the tail in order 1, but then to, let's say, what's the way to say that? Okay, this is, yeah, access wasn't a bad word. So we can access the tail in one operation, we have a pointer to it, but then to discover the new tail, we have to traverse the whole list. Okay, so this is a traversal cost. Okay, so we can start to say, this is why not having back pointers is a really bad idea. And maybe just to round off the operations, if we are searching, say, for the value 9, and let's make our linked list L HT. This is now only pointing to 5. My linked list has become very short, but that's okay. Okay. And we want to search if 9 is in our list. Well, false, it's not in our list. Okay. So one of the things to bear in mind is whenever you search for something in a data structure but don't find it, you're probably in the worst case scenario. Okay. So then what will be the time complexity of searching for something in a linked list? It feels like I'm trying to trick people by, I've now only got a list of L plus size 1, but again, we don't care about that. We think as people are writing, yeah, log n. Okay, if you have to search a linear structure, the worst case is always going to be a linear cost. Okay, in this case, it's a bit silly because I accidentally created a permutation on my list that only had one element, but imagine there was hundreds of elements. Imagine, yeah, hundreds of elements, and you get the idea that, okay, you would have to go through this entire list, and it would cost us 100 operations just to go through it. Good. Okay. So we get this idea that despite the fact that a list is a simple enough notion, when we start to think of the time complexities and our implementation decisions, so in this case, singly linked list, it can lead to some nasty problems that if it doesn't match your application, then this can be a bad thing. Okay.